Okay, so in the first part, we have finished everything on the linear regression. So we'll start with the second part to introduce something called ridge regressions. So, and you can see one of the problem in the linear regression with and the degree of polynomials. I mean, polynomial and the polynomial and regression is, and we have problem of overfittings. So, so our solution is we reduce the degree of polynomials by doing the holding out. Find out. So our solution is basically find the find optimal D by holding out. Right. So this is the strategy. We have a talk about that, and we actually implement this. So in like today's lecture, we are going to present another general way to do it. Is and to prevent overfitting is we can penalize the magnitude of the regression coefficients. So magnitude of regression coefficients. So why this is a good idea, and I want to remind you in a previous situation, when I do the demo, you find out in the region of overfitting, and particularly when D is 19, and I showed you what is the coefficient look like. You can see they have some coefficient is positive, like 220, and some coefficient is minus 220s. So that means you can see this has a very large values of the regression coefficients. And as a result, the total norm of the regression coefficients is very large. It's more than hundreds. So that means and that gives you some indication we have a problem of overfittings. So as a result, what we can do is we can, if we can penalize the magnitude of coefficients, so that's why we have like lower weight on the and the magnitude of the coefficient. As a result, it's possible that we can reduce the phenomena of the of the overfitting. So so the approach is whole idea is we are using, and previously we have talked about if we're using residue of some square, this is equivalent to as and like negative, and the log likelihood is actually is an MLE estimator. So in like linear regression, so like this W star is MLE, so maximum likelihood estimators. So and what we can do is we can actually do some like MAP estimation. That means we can give some prior for those weight. So, and this is additional things is we assume PW has prior distributions. So that means PW is equal to a Gaussian distributions with W as a zero mean and lambda inverse identity of D as the covariances. So this is the covariance, this is the mean. So this is my prior distributions. So this is a zero mean and a Gaussian prior. Okay. So I mean, if we do that, so that means we have this and the log likelihood. That means we need to adding this and a contribution of the prior. And I want to know the negative log of the prior is proportionally to some like lambda of the two norm of the and the square of two norm of the weight of W. So that means if we have this prior distributions, then we are no longer working with negative log likelihood or MLE and estimation. It becomes MAP estimations. So for the and for the MAP estimation, that means and not only we have like negative log likelihood, we also have a prior and be introduced. So then I mean that will be our posterior distributions. And the log, that was a negative log and a posterior and the distributions, which is probability of, I would say, what is that? The W given the data of D, right? So this is the posterior distribution, and we have negative logarithm. So this will be negative log of the posterior distributions. Okay. This will be proportionally, I mean, if you include the negative log likelihood and the negative log of prior, so this is proportionally equal to the following. So this is actually coming from the contribution of negative log likelihood, and we have addition of lambda of negative of the prior. So then my MAP here, so MAP is short maximum A prior like posterior. So and short for MAP. This is arcu mean of XW minus Y. So this is all vector plus lambda of this. So that is called ridge regressions. So the ridge regression is we adding this lambda of the square of the two norm of the coefficients. So this is called ridge regressions. In some senses, you can think about we are trying to penalize the weight. Or in some senses, that will be, and there's another name for this ridge regression. It's called Tikhonov. And the regularizations. So this term is called like Tikhonov. and the regularizations. And in general, we assume this lambda should be and bigger than 0 is our penalty, like, and the parameters. So it's penalty parameters. Okay. So that's why we can and rethink everything is we denote this whole loss functions as, so my loss functions becomes as a function of the parameter lambda and also a penalty parameter. So, and I'm as a function of my parameter like W and the penalty parameter lambda. So this becomes XW minus Y plus lambda squared. And the key here is if lambda is strictly positive, we can show this whole loss function is strictly convex. And the solution exists and unique. So even X is not full rank. So you can see this is a even stronger statement. Previously, in the linear regression, if X is not a full rank, then so loss function right here, and without this term, is not strictly convex, and then the solution may not unique, because we're trying to work with X transpose X, I mean inverse of X transpose X. If X is not full rank, then X transpose X inverse doesn't exist. But in these cases, with the ridge regression, no matter what kind of X that you are working with, there always exists the local minimum, and this local and minimum is always unique. And regardless the property of X, whether it's a full rank or not. So this is really, really strong statement, and it's really appealing in practice. That means we can always adding a tiny bit and a lambda, and to ensure so the solution is unique and exists. So you can think, and this also can help you to like regularize and the solution a little bit more. But you can think about lambda is like a tuning parameters from 0 to infinity. So lambda is being using different color here. So lambda is like 0 to infinity. So situation in two extreme, if lambda is it should be 0, so this is just a least square. If lambda is infinity, that means the first and the log likelihood, like negative log likelihood, doesn't matter. It only matters is second term. For the second term, so that indicate my W is always equal to 0. And in particularly, the larger lambda is, the more parameter up like and penalized. The more parameters up penalized. And like less flexible of the models. And think about it this way: if it is less and flexible, it will be like less overfittings. I mean, it's more flexible, it will be more likely to overfit. So, and sometimes we want our model to be less flexible, and it, like too much flexibilities, it's not good. I mean, just give you some overfitting problems. Okay, and the gradient with respect to W, it's fairly straightforward. I mean, this whole thing right here, you can think about as W transpose W, right? I mean, if we think about W as a column vector. So this is actually give you 2 times X transpose X W minus X transpose of Y. Wait, missed one term. Plus lambda W. And I believe you have done like that kind of similar exercises again in the previous courses. So we're going to assign this to be 0. This tells me that we can rewrite things as X transpose X plus lambda of identity multiply and a dot W equal to X transpose of Y. So this identity is of a size of D by D. Okay, so that means my MAP is equal to X transpose of X plus lambda identity of D inverse X transpose of Y. Okay, so you can see why this always has a solution. I mean, the only difference is between the least square versus the ridge is we have this additional term inside of this X transpose of X. So as a result, whether X transpose of X has a 4 rank or not doesn't matter, because once you add lambda of the identity of D, this whole thing right here is always 4 rank, regardless the property of X. So you can see this is quite important. And of course, that's the way, and you can think about this whole thing is always positive definite. So that's why it's always 4 rank right here. All right, so and this is the matrix form, and also there will be an index form. So equivalently, you will have index form as the following, which is xi of xi transpose plus and summation of xi and xi transpose I from 1 to the n lambda of D inverse and the product of I from 1 to the n of x of I. So I think the y of I. So this is actually a row, and then this is a scalar. So this is a row and a multiply scalar, then you sum them together. Okay, but more convenient way is just using this notation of the matrices. And of course, we have talked about this naive method. It's bad, it's numerically slow and unstable. So what we can do is, can we turn everything into something we already solved, right? So, and what we can do is we can actually like create new things. So let's say I'm going to create my x cubed. I mean, the way to solve it. Solve it. And the way we do is we're going to create a new and data of x2, which is x, and we put a square root of lambda. Okay, so what is this lambda here? So this lambda, square root of lambda, is a diagonal matrix that you put a square root of lambda on the diagonals. So this is in a diagonal matrix of R big D by R big D. And then we have little y here. Y2 is the y, and I have a bunch of 0 of D by 1. Okay, so now this whole thing is actually, you can think about this is m plus D times D. So this is R m plus D. Right, so this is the major differences here. So we basically adding some virtual data to the data matrix and the feature matrix, and adding like bunch of zeros to the target. And we show, and I want to say, if we create this way, then my MAP is nothing but my x2 transpose of x2 of inverse x2 transpose of y2. So this is just the least square solutions. So that means if we adding those like virtual data to x and y's, then we can solve everything by least square. And as a result, this is the solution for the ridge regressions. Why? Let's just look at that. In terms of this new x2 and y2, the loss here will be y2 minus x2 of w transpose of y2 x2 w. So this becomes the following. So y minus x2, x times w, and 0 minus 0 minus square root of lambda times w transpose. Then multiply y minus xw, 0 minus square root of lambda w. Okay, then we like actually multiply them out. This is becomes y minus xw transpose y minus xw plus w transpose lambda w. Okay, so this is basically the same as y minus xw square root of 2 norm plus my lambda here is and so as I think a better way to do it, just to call this lambda here. And we can actually factor out this is lambda of identity of D. All right, so this is lambda of W transpose W, which is just the 2 norm, square root of 2 norm of W. So this actually precisely equal to our loss function here. So that means these two are equivalent. So this just show the loss function for the virtual data is equivalent with the loss function of the ridge regressions. So that's why this solution right here actually give the solution for the ridge regressions. So that's good. I'm going to show you how we actually implement that. So it's important. So this is just a couple line of the code right here. So so the key here is here we're using the like P inverse. We can using this QR solver if we need it. That's quite straightforward. But the code is quite straightforward here. So the key is we are adding the square root of lambda on the bottom of x and adding a vector of zeros on the bottom of y. Then this will be my ridge and basically my ridge solve. I mean, if you're using this QR, you can just turn and unmute this part. This will be the same, I believe. Okay, so this will be the same. So this will be the QR solver. All right, so I mean, everything is the same right here. So this is, we create the data here. Here, we're just try the 10th order of polynomial. And it just, and the starting point, we know if d equal to 10, it's obviously in the region of overfitting. We are using the strategy of holding out. So that means we are going to split our data into training and testing. And of course, the question is, how can we choose this lambda, right? So this, and the way that we do is we're using this holding out methods to actually find out the optimal lambda in these cases. So we're going to using this like log search and a search for lambda values from from 10 to the -3 to like 10 to the 4th and and 5, 10 to the and 50,000. So what we do is we're going to and try all possible lambda and ranging from these values and store this testing RSS. Then we plot them out. Okay. And we only plot out the testing RSS. I mean, if we do that, we find out this is the value here. You can see here, we're just plotting the logarithm of lambda, and just to ensure everything has the right scale. So you can see the optimum lambda is chosen as I'm about 10 and the lambda equal to 10. At this value, so the minimum and RSS for the lambda is about 84 right here. And you can see this has a roughly a U shape right here. And then the minimum is and reached somewhere here. And of course, so this actually depends on how you split the data and different ways to split the data. It might give you different lambdas, but roughly those values are like are close enough, I would say. So the reason that I'm using like logarithm here is because if we don't use logarithm, all these values are being skewed because we have all these lambda here is basically in the log scales. So we can plot that out to see how and what is the and the curve really look like. You can see this is the curve really look like of my prediction here. So let's see. So trained. Yeah, this is my prediction for the training here. This is So this is the least square. I don't know why this is being flipped here. I think it should be best fit train testing. Yeah. Should be like that. Yeah, this is the blue point is training. I mean, orange point is testing. And you can see how we actually choose this and a different and the lambda here. So lambda is chosen, I think it's about 10. And you can see, so my best fit is slightly different from my least square fit. Particularly the differences is shown on the boundary here. Right, so you can see on the boundary it has some slightly and differences, and it will be and slightly and different from least square. And you can see from just from this scale, it's quite. I mean, overall it's quite quite different here. Okay, so and this just give you how and give you some idea and of this problem that we are working with. Okay, so and of course we can try this with the scikit-learn packages, but I want to warn you, and you shouldn't do that. And for this courses, and later on 593, and you're going to use this again to actually to demonstrate this whole idea. You can see this is actually using this plot right here. So you can see I think in this case is we using let's -10, that's too small. Let's try it like -3 to maybe 4 right here. So you can see the testing error is that so the MSE on this case, I mean, if we have like large regularization, the wait. Oh yeah, so the testing, you can see this testing error has this like U shape right here, and then the minimum is reached somewhere about 0.1 and 1 right here. Okay, so this is just coming from the scikit-learn. It use different ways of, to approach. It just give you some idea and what kind of problems you are working with. Okay. I mean, it's basically the same. The reason why the result is different is just because and the way actually you split the data, because we only have very like small amount of data, and how you split the data actually matters. So that's why you will see and different like optimal lambdas again. All right. Okay, so another thing that I want to talk about is wait. Okay, so here, that's good. Is like additional and the way of to do the cross validations. Previously we're using holdout, but holdout, it turns out it's not very good if your size of training data set is small, because you can see if we change the way that we split, it turns out and the result, could fluctuate. So for holding out approach methods, will gives unreliable estimate of parameters if if training set is small. So in this case, it's less than 100. It actually depends on which 20% that you choose on the validation set. And it could make a huge differences here. So another way that we can like get around this is we can and work on this something called k-fold cross validations. So another way that we can work out is it's called k-fold cross validations. So what is k-fold cross validations? It's the following. Okay, so I'm going to tell you and specifically, but this works well when data set is small. So this is particularly works on the situation that your data set is small. So first thing is I'm going to say you need to pick k. K, let's say set k equal to 10. So then you are going to split the total data. Okay, let's set k equal to 5. Okay, and I set and so the first thing is we split the whole data into training and testing. So this is, and for example, what we can do like 90% training, 10% of testing. At this point, we will completely leave this testing data set out. We're not going to touch that. We're going to, so we are not going to use this 10% of data at all during the training process. So key, never use testing data during training process. Otherwise, you will be cheating. Right? So this is a clear cheating and the problems right here. So the first thing that you need to, and always to remind you, never use testing data set during the training process. The second thing is you split the training data into k-fold. And for example, in this situation will be 5-fold. So basically, if we are and splitting the data, we are splitting the data into 5 parts. So, and this is just for the training data, right? So this is for 90% of the data. And out of this 90% data, we are going to split this into 5-fold. Okay. So then for each fold, k, and this k is from 1, 2, 3 until k, and big K. We train all the fold. And so we train on all the fold, but the kth. And then validate your result on the kth fold. So, and this is done in the round robin fashion. So, and what does that mean here? Is for this and 5 set, this is we are doing this. And for example, for the first time, we are using, this is validation. And these 4 are training. So this is the fold and first one. So then you do it for 5 times. And for example, the second one, I'm going to draw it one more time. So you're going to, this will be your validation set. And the rest of that will be training. So you do it all the time. The last one will be the first, right here will be validation. So you do this 5 times. And everything else will be trainings. So that means each fold are being used once and only once for the validations. So this is kind of like something called round robin fashion. As a result, I can define something on ERM, like empirical risk and minimization. So this is basic says I'm going to sum all these k-fold validation results together. So this will be R lambda CV. That, and since we've done it k times, we're going to and divided by k. Okay, so this will be RK. So we find out theta lambda hat of D minus K. So that means it's, we trained on all fold but K. So this is, we find out optimal theta hat, but evaluate at the DK, which is my validation data set. Okay. So this is all other data. So this is the K fold. As a result, we find out so we go through all possible and a lambda here. We find out the best lambda, which is argue mean of lambda of R lambda CB. Right, so this is, but previously, holding out, we only do it once. But here in k-fold cross validation, we do it like k times, and we average the validation error together. So this will be our our lambda here, and like an optimized lambda here. At last, we combine all the training data. And re-estimate these parameters. So this is becomes, so we fix our lambda hat, then we re-estimate this theta hat. This will be argue mean of theta R lambda hat, theta and a D train, I would say. So we never actually and use testing data on these things. Then apply on testing set. To assess the accuracy. So you can see this is how it's being done. So we actually need to separate out this 10% data set to actually assess these accuracies. Okay. In this whole idea, never train or choose parameters based on testing data set. That will be cheating set. So basically, never train or choose parameters based on the test set. Otherwise, you'll be cheating. So this is very important. All right. And of course, and we can choose all sorts of different n. For example, here is one of the examples. We can choose n equal to like n number of points. This is something called leave one out cross validations. So basically, we always train on the n minus one items and test on the remaining one. That could be very expensive if n is very large. This is basically what we have talked about. This is fivefold. Just tells you this red right here is the validation set. Everything else will be training set. So we do exactly the same thing. So this is basically, here we're adding more like testing data set, 200 more points. Just give you some idea. And we do some feature scaling because X actually, have a big issue is this X has very, and it scales like varies too much. It's very hard to handle sometimes if you have that kind of situation here. Again, we're choosing D equal to 10. This is a situation that we like work out. So here we are, and just using this minimax scalar. So this is just to rescale your data between and based on the minimum and the maximums. So can be worked out, and the value is just between 0 to 1s. All right, so yeah, it's like 0 to 1s. So here we are choosing like k-fold k. Equal to. That's really a lot to, and let's just choose 5. So what we do is we need to find out the number per fold. So that means we need to split this data into each fold. Each fold that should have that many amount of data here. So then we are working through with the 2 like double loop right here. Here we are using slicing to calculate the index of training set, and the validation set should be. Here the ith fold will be the validation set. So basically we move out the ith fold, and the rest of things will just naturally becomes a training set. So this is we work out this training set and work out this validation set. Then we apply this read and rich QR, and this will be my W hat, and this will be my predictions on the validation data set. And then this will be my here I'm using MSE, and this will be you adding this MSE errors for this fold of the validation set. At the end, you are going to divide it by the number of the K right here. If you do this, you will find out the value looks like this. Okay, so this actually, I think we changed this lambda from minus 5 to 2. So I'm going to take the logarithm here. So I think it's logarithm. Let's take the logarithm here. Just to ensure everything is. Yeah, so the logarithm here. So the logarithm here, you can see it start to like moving down and then like start to increase here. The logarithm here is actually tells you the minimum lambda here, MSE in lambda. If we choose k-fold k equal to 5, is about 4, then the optimal lambda should be 0.0035. So with this k-fold, this is always very, very reliable. This is always give you very and very close result. And in that cases you are and you should getting more like stable result rather than and the holding out result. And you can compare the performances with training MSE and testing MSE. So you can see for the training MSE right here, if we're choosing this L best, which is about 3.52, and the testing MSE is 4.08. If you see this like testing MSE is slightly larger than training MSE, it will be good. But if you see the testing MSE is much, much larger than the training MSE, it might have some overfitting issues. But from here, you can see this and testing MSE is reasonably good, but I mean it's like seems a good fit. But if we actually look this W here, this has like no close to this like true ones. But if we actually plot them out, you can see it actually worked pretty well. You can see this scales pretty well. It looks like yeah, I don't think that's a leave one out cross validations, but this and our best fit. And you can see this actually has a really good fit. I mean the cases here. But of course, we have to be careful. And because we have scaled our X right here, when we actually plot them out, it should be and scale back for the and for the original X test right here. All right, so so this is the k-fold cross validation. You can see this actually gave a really good fit. I mean, despite we choose d equal to 10, although this coefficient doesn't mean anything, but I mean, in terms of performances, it does actually have a really good result. Let me just plot out the yellow points as well, just for the testings to ensure the differences. I think it's right here. Plotting X test. Oh, yeah, that's already X test here. Oh yeah, that's the just the in the fit already. Y test. Okay, so Y test scatter train test train, right? Wait. That's not good. Did I change something here? Oh, X test right here. X test 0. Y test. Okay, so X test. Y test. Y test. Okay, let's see. Oh wait, that's did I do X? Yeah. Okay, so I think everything is scaled, so that's why it looks weird. Um, yeah, I think I'm everything scaled from 0 to 1 right here, so that's why it looks weird here. So let me just like and replace this everything into the best fit. That's the testing data set. My bad. Okay, so this should be good enough. But you can see this is I mean it's quite and fitting the data very well. So that's good. Okay, so here is I'm a little bit summary for everything. So and a particular so with the and various different strategy. First is holding out. We basically split your data set into training and a validation set. Detrain and devalidations. We usually use 80%, 20% split. So basic whole idea is we fit the model in the detrain for each setting of lambda, then evaluate performances on the devalidations. Then we pick the value of lambda such that it gives you the best validation performances. So this is very easy to set up and it runs very fast. But the problems is when the data size is small, lambda won't be reliable. It might vary a lot, depends on how you split the data set. Then this error and testing error or validation error will not be reliable since we are actually using part of data set during fitting. So this should give you some guidance, but that doesn't mean you are getting the true testing error. So this is something that you have to keep in mind. And we also talk about k-fold cross validation. So that basic says we split your data set into training and testings, and the basic is 90% of training, 10% of testing. Then we further split the training data set into k-fold. K could be 5, could be 3. We train auto-fold, but the k and validate on the k in a round robin fashion. Then we average error for those k-fold pick, and to pick the optimal value of lambda. In this case, lambda is always reliable, and test error is also reliable because we never use this test data set during any process of training and validations. So this is truly the new data set. But this setup and algorithm is very complicated, and the time cost could be super big if your data set is large. Even k is relatively small. If your data is tens of thousands, you shouldn't choose k more than 3. So this is something that you have to keep in mind. There's a compromise between k-fold cross-validation and holdout. Is basically, you can think about k equal to 1. It's 1-fold cross-validation. So the way you do is you split your data into training and validation and testings. Here, we're doing 80% training, 10% of validation, and 10% of testing. So this is in the middle between k-fold and holdout. So it's basically we fit the models on the training for each setting of lambda, then evaluate the performance on the validations. Then we pick the value of lambda that resulted in the best validation performances. And after that, we find out the best lambda in the model and apply to the testing data set to find test error. In this case, this test error will be reliable because we never use that test data during building up the models. But of course, we have the same problem as holding out because if data is small, this won't be reliable. And also the setup and the whole process will be more complicated. So, and a lot of cases, if your data is median, we can just using this cross validations, I consider as a 1-fold cross validations. If the data is super large, millions, and holdout will be fine. Cross validations work about tens of thousands. That would be ideals and among the data set. A k-fold is usually about 100 to thousands data sets. Then you can choose k equal to 3. That would be a perfect way to work on k-fold cross validations. So this gives you a very good overview of these 3 ways to choose the optimal parameters. Holdout cross validation, k-fold cross validations. At different situation, in the homo projects, you actually need to find out the and which one can fit the best, right? So it depends on your problems, depends on how large of your data that you have. All right, there are 2 questions that I left here for you to think about this, to think about why this is wrong, why this is correct. In the later of the courses, we are going to discuss this a little bit. I will leave. So I will leave this for you to think about this. All right. So that's all for that.